Let's start this lesson with a high-level overview of DevOps environments. Most companies have several environments for development, testing, and production deployments. The number of environments a company has can vary based on few factors. It might depend on the software development policies or simply how much money the company wants to spend. This lesson covers Kubernetes deployments, but the same principles can be applied to other platforms and systems. Now, it's very common for a company to have the following 5 environments in some form. However, they might be called by different names. First of all, we have sandbox environment. This is isolated environment used for experimentation, learning, and testing without affecting other environments. Next, we have development environment. Here, developers integrate their code with other deployed applications and microservices. Next, we have testing or QA quality assurance environment. QA personnel are dedicated primarily to testing new features and environment as a whole. The goal is to split responsibility and let other people test developers' code. Once approved, application moves to the next stage. Next, we have staging or pre-prod environment. This environment should replicate your production environment as much as possible. The data setup should be similar in scope and size to production workloads. In this environment, you should not only test your applications, but also verify that the infrastructure operates as expected. Finally, we have production environment where you release your applications and handle real data from real clients. This is a protected environment where access is assigned based on the least privilege principle. Sometimes you don't want to spend a lot of money maintaining many different environments. So how can you reduce the cost of your infrastructure? Also, different companies have different release cycles. For example, some might deploy to production every day or even multiple times a day. It's rare, but it happens. Other companies may deploy to production every week, others every month, and so on. It heavily depends on the type of software you develop and internal policies. So let's say you deploy to production every week on Wednesday. What you can do is to allow all your developers to continuously deploy their applications to development environment until Tuesday. Then on Tuesday, you would freeze your development environment, turning it into a staging environment. By freezing, I mean pausing all new version deployments in that environment. Then you would ask your QA team to test individual applications as well as environment as a whole. After they run all the tests, whether automated integration tests or manual validations, you would take a snapshot of those deployed versions and prepare a production push pull request. In this video, I'll show you how to use GitOps in practice. We will automate freezing, unfreezing, and production pushes using a script. For example, if you want to freeze or pause continuous delivery of a service using ArgoCD, you would need to add ignore annotation to the application resource. If you have hundreds of microservices, you would need to automate this process. In this video, we'll create a GitOps script that you can run manually or preferably using Jenkins or any other tool. When you run the pause command on the development environment, this script will create a new branch in the remote GitHub repo. It will go over each application resource in the target environment, add ignore annotation, and create a pull request. It doesn't matter if you have 2 applications or 100. Then you can share this PR with your teammates, wait for their approval, and merge it to freeze the environment. This is GitOps in practice. Then you would run the script again, this time to prepare production push. You select source environment like development to take the latest deployed versions that were tested together by your QA team. Then select target environment, in this case production, to create a pull request for the production push. Then the script will create a new branch, update all applications with the latest deployed versions from the frozen development environment, and prepare a production pull request. On Wednesday, after all stakeholders approve the pull request, you would merge it. If it breaks your production environment, you can quickly revert that pull request. Finally, after a successful production push, you can unfreeze or resume continuous delivery to the development environment. This script will prepare another pull request to unfreeze your environment. Once you merge that PR, the staging environment will be converted back to development. Developers will be able to automatically push their code to that environment. In this video, we'll use ArgoCD for continuous delivery, but the same logic can be applied with FluxCD and other GitOps tools. First, we'll use the App of Apps pattern to bootstrap our development and production environments. In the development environment, we will configure continuous delivery using annotations and use private ECR repositories to store our images. First, we need to deploy ArgoCD image updater and authenticate it with AWS to periodically check for new image tags in ECR repositories. To do this, we need to create a dedicated IAM role for the image updater with read-only policy to get tags from ECR. Then we'll use EKS pod identities to map IAM role with Kubernetes service account used by image updater. And finally, we'll create and mount a simple script inside ArgoCD image updater that it can use to obtain a temporary token to access AWS and list new images. You can use OpenID Connect provider as well. The logic is exactly the same. However, the best practice is to use pod identities. Since we're using App of Apps pattern, we also have to use Git writeback method. With this approach, when ArgoCD image updater detects a new image tag with a new version in the ECR, it will clone repository, create a new commit for each service with the new version tags and push it back to GitHub. The default interval for the image updater cycle is 2 minutes. Independently, the main ArgoCD server will detect a new change in the Git repository and synchronize the state in the Git repository with the state in the Kubernetes cluster. I'll show you step by step how to implement all of this, and we will frequently test as we progress so we can catch any issues as soon as possible. I also have ArgoCD tutorial for beginners if you want to start from scratch and try Helm, Customize and plain YAML deployments. First of all, we need a Kubernetes cluster to play with, preferably in one of the major clouds such as AWS, GCP or Azure. However, if you want, you can even spin up a local Minikube cluster to test GitOps in practice with a few changes. But if you want to follow along, you can clone my public GitHub repo, where I have all necessary Terraform resources to create EKS cluster. Additionally, I have a full Amazon EKS course on my channel that you can take if you want to provision a production-ready Kubernetes cluster in AWS. I'm not going to explain all the details related to EKS in this lesson. At this point, we have Terraform code to create a fully functional EKS cluster, and next we need to deploy ArgoCD. ArgoCD itself does not require any special permissions from AWS, so it's quite simple to deploy using a Helm chart. First, we need to initialize Helm Terraform provider. If you want to try this locally on Minikube, you can use static credentials. In AWS, we use data blocks to get EKS cluster and authenticate with it. By using data resources, Helm provider waits until the cluster is ready before installing any Helm charts. Authentication with a token is preferred because it doesn't require any dependencies to be installed on the host machine where you're running Terraform. Next, we need to provide authentication mechanism for the pods running in Kubernetes to access AWS API. The oldest approach was to attach all IAM policies to Kubernetes nodes. Then EKS introduced OpenID Connect Provider and web integration. And finally, the simplest and recommended approach is to use EKS pod identities to map IAM roles with Kubernetes pods, specifically with Airbag service accounts. It's very easy to implement. You can use EKS managed add-on and install EKS pod identities agents using a single Terraform resource. It will be created as a daemon set running agent on every single Kubernetes node. You can run the following command to get the latest version of the add-on. Also, you can check if it's compatible with your EKS version. Well, most likely it will be. Alright, let's go ahead and deploy ArgoCD. We'll use Helm to deploy it and override a single variable. First, create a values folder. Next, create argocd.yaml file. For this tutorial, I only want to disable TLS on ArgoCD UI. ArgoCD instance almost never needs to be exposed directly. Instead, you would use ingress and secure it with TLS if necessary. Without a TLS certificate for ArgoCD itself, you avoid the warning about insecure connection and the additional step to access UI. Next, we need to deploy ArgoCD Image Updater. This service monitors Docker images for new tags and can optionally update those applications in Kubernetes with new tags. Well, Image Updater needs access to private repositories, such as ECR. In the previous lessons, I explained how to authorize Image Updater with private Docker Hub repositories. In this lesson, we'll authorize it with a private ECR, Elastic Container Registries, in AWS. First, we need to create IAM role with IAM policies to trust pods in EKS and allow them to assume IAM roles. This resource creates IAM policy. Next, we create IAM role itself and attach that policy. Now, we need to grant access to ECR. You can use a custom IAM policy to limit access to specific repositories. However, it's more practical to use a managed IAM policy and grant read-only access to all ECR repositories in your account. Next, we need to associate this IAM role with a specific Kubernetes Airbag service account and specify the namespace. Our ArgoCD Image Updater will use this service account and will be deployed in the ArgoCD namespace. It's very important to configure this properly. If not, Image Updater will encounter permission denied errors. If you discover any access-related errors later, this is the file you need to double-check. Finally, let's use Helm to deploy Image Updater. Optionally, you can use depends statement to deploy one Helm chart at a time. I discovered that deploying a bunch of them simultaneously might cause errors that could break your pipeline using this specific Helm provider version. Next, we need to override some default values in the Helm chart. First, we need to specify the service account and not rely on Helm to generate one. This exact name is used to establish trust between AWS and Airbag in Kubernetes. Alright, now before adding additional configurations, let's create a couple of ECR repositories. Let's call the first one users and keep it private. The second one will be payments for another microservice. So far, we have two repositories. Now, for the next configuration, you need to copy this string that contains AWS account number along with the region. But before that, let's create a script that the image updater will run to authenticate with ECR. It's a very simple one-line command that you can test locally as well. Just make sure to update the region. This command will obtain a temporary authorization token and decode it using base64 utility. Let's run it locally to verify that we can get a token. Usually, if you were able to run Terraform, you have wide enough access to run this command. Alright, it works and we have the token. Next, we need to configure ECR repository. Replace my repository URL with yours by copying and pasting it from AWS console. You can also dynamically provide these variables in Terraform using template built-in function. The script will be mounted to the /scripts/auth.sh path, and the image updater will run it every time token expires. Alright, that's enough Terraform for now. Let's go ahead and initialize it. Then we can apply it. Creating EKS cluster from scratch may take up to 10 to 15 minutes. The first step after you provision EKS is to update your local Kubernetes config to get access to EKS. In my case, it is deployed in US East 2 region, and the name of the cluster is environment prefix followed by the demo. Let's get all the pods in ArgoCD namespace and make sure that all of them are running. Next, we want to verify that we correctly configured EKS pod identities. This step is optional but helpful. First, let's SSH into ArgoCD image updater pod. Then we want to execute the same command in the image updater pod, or you can just run script itself. It's up to you. When you run it, you should get the token as well. If you get error such as you should run AWS configure or any other permission denied errors, first try to restart the pod. You can just delete image updater pod and wait until Kubernetes replaces it with another one. When it's ready, try to SSH and run the script again. If you get the same error, it means you misconfigured your access and should double check IAM roles and pod identities configurations. Also, let's verify that we can access ArgoCD UI. First, you need to get admin password that Helm chart generated and stored in the admin secret in the ArgoCD namespace. The easiest way to expose your ArgoCD for testing is to use port forwarding. Now, let's try to access it. The username is admin and the password is the one generated by the chart. Alright, we have a fully functional ArgoCD and image updater. The next step is to create a Git repository that will contain all the Kubernetes applications. Let's call it something like Gates and make it private. You can add README as well. There are a few ways to authorize ArgoCD to pull this Git repository. You can use a personal token, application tokens, or my favorite and the simplest approach, creating a deploy key. It's very generic authorization method based on SSH key and works with other repositories such as GitLab and Bitbucket. First, we need to generate a key pair locally. Don't provide a passphrase for this key. Alright, now we have a private and a public key. Next, we need to upload this public key to GitHub. This key can be public and anyone can access it. To upload this key to GitHub, go to Settings for the specific repo. On the left-hand side, select Deploy Keys. Give it a name, something like ArgoCD, and paste the public key. Now, since ArgoCD image updater will need to write back to this repository, we need to enable write access. Alright, we have a deploy key with read and write permissions. The next step is to authorize ArgoCD deployed in Kubernetes to clone that repo. For that, we need to create a Kubernetes secret that contains a private key that we just generated. Well, There are many ways to securely store those secrets. For example, in the previous lesson, I showed how to use sealed secrets and store those sealed secrets in Git repositories. In this lesson, I'll create that secret locally and apply it without storing it in Git. Preferably, you would use some kind of integration, maybe AWS Secrets Manager integration. I also have a tutorial on how to implement that and place the secret in Kate's repo, so that if someone accidentally deletes the secret, it will be immediately reapplied. Now, the name of the secret doesn't really matter. The most important part is that the GitHub URL must match your Kate's repo, and don't forget to replace my username with yours. Next, copy and paste the private key that you generated. This is your public key. And this is your private key. Next, we need to apply the secret to Kubernetes, and ArgoCD will use it to clone the Kate's repo. Alright, we're ready to deploy a few applications to Kubernetes. Let's go ahead and clone this repository. Open it using your favorite text editor, in my case, VS Code. Now, let's start by creating a folder structure for our environments. First, create a top-level folder called Unfreeze. Second, create a folder for the Helm charts. You can use Helm charts, customize, or both. With the image updater, only plain YAML Kubernetes objects are not supported. If you want to use YAML, you should switch to Flux CD. Next, switch to the Helm charts folder and generate a few charts. At this point, make sure you're using exact same names for the folders. This will be important for the GitOps script. Later, you can update and rename them after you make it work. First, generate a Helm chart for payments application. Next, generate another one for users microservice. We're going to use them as is. We have a bunch of template files to generate Kubernetes objects. We also have a default values for Helm, and we're going to override a few of them. First, we'll provide a Docker image and a tag for each microservice. Additionally, our app runs on port 8080, so we need to override this part as well. Finally, we will provide a custom health check endpoint, which is /healthz in our case. We'll do this for both payments and users microservices. Now, under Unfreeze folder, let's create a couple of environments. First, we need a development environment where developers can deploy their code and test. This environment will be converted into staging for a short period of time for testing before we release those application versions to production. It's a good compromise if you want to save money on your infrastructure. Second, we will have a separate production environment. You may have more than one production environment, perhaps for different clients or in different regions. Next, let's create a folder for each application. It's not strictly necessary, but we need these folders for the script. We're going to deploy 2 applications, so we need a folder for each of them. Alright, let's create application resource to deploy payments application first. Let's start with annotations. These are very important for configuring continuous delivery, so be very careful and pay attention. This is a development environment where we want to enable image updater to continuously watch and deploy new Docker images. This is done using image list annotation. First, payments is an alias we'll use in other annotations to reference this image name. Then the image itself. You need to copy and paste it from the ECR page in AWS console, and this specific image does not have any constraints on the image tags. This, along with the default semantic versioning update strategy annotation, will instruct image updater to update this application to any latest image tag it finds in ECR. And of course, we need to set writeback method to Git. This way, image updater will detect a new image tag in ECR, create a new commit in Git repository, and let ArgoCD server synchronize and apply it to Kubernetes. Keep in mind that the default writeback method, which does not commit changes to Git, does not work with App of Apps pattern, which is very important for bootstrapping the cluster. Otherwise, you would need to manually apply all your applications to Kubernetes. Next, let's add a finalizer that will allow us to delete application resource and wait until your application is removed from the Kubernetes cluster. Otherwise, when you delete application resource, your application will keep running in K8s. Then give it a name like payments-dev. We'll use the same cluster to deploy development and production environments. In real life, you would frequently have a dedicated Kubernetes cluster for production and sometimes even a different AWS account for production environments. For the following demo to work, make sure you're following the same pattern. Use application name like payments with environment suffix. For now, just keep using the same naming conventions because our script relies on them. Later, you can update GitOps script. We also need to create application resource in the ArgoCD namespace. Next, we have destination block. Potentially, you can deploy applications to remote cluster. You may have a single Kubernetes cluster located in central location or environment, and you can use that single ArgoCD instance to deploy applications in other environments in different Kubernetes clusters and even different AWS accounts. In this lesson, we'll be using ArgoCD instance located in the same Kubernetes cluster where we deploy microservices. Let's use dev namespace for all applications deployed in development environment and prod namespace for all production deployments. Usually, you would have a separate namespace for each application. Also, let's keep default project. At this point, we need to override some Helm specific values for the vanilla Helm charts that we have generated. First, let's update image name to payments. Make sure you're using your own repo name. Then update port to 8080. Next, set the health check endpoints. I have another video explaining the differences among all types of health checks on my channel if you're interested. Finally, set initial image tag to 0.1.0. We'll use the same tag in production environment to bootstrap our cluster. That's pretty much all for the Helm values. Next, provide the path where the base Helm chart is located in our K8s repo. It's going to be under Helm charts folder. Also, provide URL to clone this repository. Make sure using the same URL that you used to create Kubernetes secret with the private key. These two URLs must match. For the target revision, you can use a branch name or head. Next is the sync policy. First, we want to prevent human errors and not allow applications to have empty resources. By default and as a safety mechanism, automated sync will not delete resources when ArgoCD detects the resource is no longer defined in Git. Let's set it to true to remove the application from Kubernetes as well when you delete this application resource. Also, changes made to the live cluster will not trigger automated sync. In that case, you would need to manually click sync from the ArgoCD UI or use CLI. This is not what we want. We want to completely manage our deployments using GitOps by creating and merging pull requests. So let's enable self-healing to automate this. For the sync options, we want to validate YAML first. For example, if you misspelled something in your deployment object, we don't want to apply it. For a certain class of objects, it is necessary to disable this check. Examples of this are Kubernetes types that use raw extension, such as service catalog. We also want to create a namespace for the application if it doesn't exist. We want to delete all the resources in the foreground to be safe. You can also set it to background, and orphan option is also supported. Finally, the prune last feature allows resources to be deleted as a final implicit wave of sync operation after other resources have been deployed and become healthy, and after all other waves have completed successfully. Alright, this is application resource to deploy payments microservice to Kubernetes and continuously update it using new image tags from the ECR repository. When you get to this point, make sure to update git URL to point to your repository. Also, make sure to update ECR repository name. Do the same in the annotation. If you have different names, update the aliases as well. Or you could use a generic alias name for all application resources if you have only one single image in your deployment object. And of course, use environment prefix and deploy it in the dev environment. Now, let's quickly create another application resource for the user's microservice. It's very similar to payments except for a few parameters. Obviously, we need a different image for the deployment, which is called users. Also, we need to replace the image in the annotation. In this case, we'll use semantic constraint on the version we want to deploy. The first is the major version, then the minor, and finally patch. For the users application, we want to automate updates only if we have a new patch or minor version. We don't want to deploy users Docker image if the major version has changed. The reason for this constraint could be that the user's microservice changes API interface that other applications use to interact with it. By disabling auto-update, we can prepare and synchronize other dependent applications to be deployed without breaking development environment. This feature is optional, but sometimes useful. Next, let's copy and paste these application resources along with the folders to the production environment and make some changes. The main change we want to make is to disable any automated deployments. It's very rare for the companies to have automated deployments all the way to production. It is possible for some small, not critical microservices, or perhaps for startups, when your service can be broken occasionally. But it's totally not acceptable for companies that have large customer base, especially if your customers are other companies or even government agencies. So let's disable CD for the payments first. Go ahead and delete all annotations. We don't need to monitor any images or write back to GitHub since there are no automated deployments. Also change environment from dev to prod. And start with a 0.1.0 application version in production environment. The rest of it can remain as is. Next, make the same updates to the user's application. First, remove all annotations. Then, replace dev with prod. That's all we need to deploy payments and users' applications in the production environment. Alright, so far we have the following structure. We have environments and Helm charts top folders, as well as folders for each application inside a specific environment. Let's go ahead and commit all the changes. Then push them to the remote GitHub repository. Let's double check that we have Helm charts for our applications and we have different environments under envs folder. Make sure you have the same structure for demo to work. The application folder names don't matter. Our script will go through each folder under the environment and collect metadata, regardless of how many applications you have or what you call them. This is our K8s repo with all applications. Now we need to switch to the previous project where we have Terraform code and Kubernetes GitHub secret. Let's go over this simple app. We have a single Helm endpoint. That is a naming convention from Google deployments to prevent clashes between Kubernetes endpoints in this case and internal application endpoints. We also have a simple Docker file, almost ready for production, and a requirements.txt file with all the versions to build reproducible Docker images. Let's switch to the My App folder in the original Git project and build Docker image. We'll use the same image for both payments and users applications. I'm on Mac with Apple Silicon, so I need to provide the platform to build Docker images for EKS cluster, unless you're using Graviton instance types for Kubernetes workers. Next, we need to authorize Docker client to push to ECR. The easiest way is to go to your repo and copy provided command. Now, we can tag payments application with 0.1.0 tag. Let's tag users application as well using the same myapp 0.1.0 image tag. Next, let's push payments image to the ECR repo. Let's also push users image. So far, we have two ECR repos for the payments and users microservices. We only have a single image tag for both services. It's important not to push additional images with new tags for now. Alright, we're ready to deploy applications using App of Apps pattern. This means we create a single application resource that manages all other application resources specific to our microservices. This main application resource uses kubectl to recursively apply the entire environment folder. It's similar to a regular application, but instead of a Helm chart, we provide a path to the entire environment folder. In this case, the dev environment. It's important to set recursive to true, so it applies all subfolders with our applications. We'll use environment as a prefix and use the same finalizer to delete entire environment if this application is removed from the cluster. This is a typical setup, and we'll use the same GitHub URL for the K8s repo. Another difference is that we don't specify destination namespace, since all these application resources themselves, not Kubernetes deployments, will be created in the ArgoCD namespace. I'll copy and paste the same application resource for the production environment. Just rename dev to prod, and that's it. Make sure you port forwarding ArgoCD so we can access UI. So far, we don't have any applications deployed using ArgoCD, so let's deploy applications to development namespace. We only need to apply a single app. That's why it's called App of Apps pattern. You might get warnings about finalizer naming, but there is nothing we can do about it. It's up to ArgoCD to update and release a new version. In the UI, you'll see that app-dev was created first. Then the rest of the applications will be applied and deployed to the dev namespace in Kubernetes. Before moving forward, make sure there are no errors in the applications and that all of them are healthy and sync. You can also open one of the applications and double-check the version used to deploy the service. It should be version 0.1.0. Next, let's apply production environment. For the bootstrap, these steps must be done either manually or as a part of your pipeline or script to provision your Kubernetes clusters. On the right-hand side, we'll get production applications. At this point, it's exactly the same as development, and both environments are now using 0.1.0 image tags. Before continuing, make sure all apps are healthy and sync. On the left-hand side, we have development environment, and on the right-hand side, we have production environment. Double-check image tags. Now, let's get the pods, and maybe use watch command to monitor them. In the development namespace, we have 2 pods, and the same in production. Before we test continuous delivery, let's tail image updater logs. It's good to tail the updater logs initially to spot any errors. If there are IAM permission issues, you'll immediately see errors in the updater logs. Currently, image updater has detected 2 annotations with images in the development namespace and is checking for new image tags. The default interval between checks is 2 minutes. I wouldn't advise reducing this limit because additional API calls to AWS can be throttled, potentially breaking your continuous delivery. If you have many images to monitor, I suggest increasing the interval rather than reducing it. As you can see from the logs, interval is exactly 2 minutes. Let's start testing our CD pipeline by releasing a couple of new image tags. We'll use the same myapp 0.1.0 image as a source. The payments application will take any new image tags, so let's update it to 2.5.0. For the users microservice, we'll release a new 0.5.0 image tag and push all these images. It will be fast since we already have the same images in AWS. Now, we need to wait up to 2 minutes for the next image update cycle. It looks like image updater detected new versions, created 2 new commits for each application, users and payments, and pushed them back to GitHub. This is why we need deploy key with right permissions. From the logs, you can see exact image name and tag. In this case, users service was updated to version 0.5.0 in the development environment. You can also see in GitHub that the image updater created new commits. By default, image updater uses Helm chart folder to commit new versions. It uses application name and environment suffix. This allows continuous deployment in different environments with different constraints. For example, you can enable continuous deployment to production if a new image tag has a specific suffix like prod, but this is rare and risky. In Git, we now have a new commit with users 0.5.0 version. For the payments, we have 2.5.0 version deployed in development environment. Since image updater committed new versions to Git, we need to wait until ArgoCD server synchronizes Git with the state in Kubernetes. The default interval is about 3 minutes, so at most we need to wait up to 3 minutes. Or you can click the sync button or use CLI to speed up the process. You can see that the last sync was 7 minutes ago, since there were no changes in Git during that time. If you don't want to wait, just click sync. I'll wait for ArgoCD to automatically perform synchronization. I'll speed up a bit. In about 3 minutes, ArgoCD detected new commit in Git and released new versions to Kubernetes. From the UI, you can see that the last sync was performed a few seconds ago in the development environment. Let's double check that the new versions were deployed in Kubernetes. Payments application was upgraded to version 2.5.0 and users service was upgraded to version 0.5.0, which are the latest versions we released. Now it's time to create our automation script to freeze environment and push new versions to production. We'll use Python for this. So first we need to create a virtual environment for our GitOps script. Then we need to activate that environment. For the script, we'll need a couple of external packages. First, we need to parse YAML files and convert them back from Python dictionaries to YAML files. Second, we'll use GitHub Python package to update files, create commits, and pull requests. You could potentially use Git package and REST API calls to create GitHub pull requests. If you use Bitbucket or GitLab, you would need to slightly update the script, but the core logic will stay the same. As a best practice, let's create a snapshot of all the package versions we used to develop the script. Now let's make sure we are in Kate's repository with Helm charts and environments. However, this script makes remote changes and does not clone anything locally, so you can develop the script in any other folder or repository. First, let me quickly create that gitignore file and ignore virtual environment. We never want to commit that folder. Instead, anyone who wants to work on the script would create their own brand new virtual environment and install dependencies from the requirements.txt file. Alright, let's start. Let's call it something like GitOps or anything related to DevOps. First, we want to select Python interpreter. Once you make the script executable, you don't need to use Python command to run it any longer. We need to import a few packages. ArgParse to provide options or flags to our script, OS to parse environment variables, and datetime to use as a suffix for branch and pull request names. Next, we need YAML package to work with YAML files, and GitHub to create remote branches, update files, and create pull requests. I want to highlight that this GitHub package allows us to modify remote content without needing to clone or change anything locally. All actions will be performed on the remote Git repository, not the local one. This means you can place this script anywhere you want. A quick warning, I'll be using a lot of repeating code to make it easier to learn and understand. For production use, you would refactor many of the functions below. The script is just to teach you the idea behind GitOps and automation. First, let's create a function that would freeze environment. In other words, this function will pause all continuous delivery in the specified environment. It takes as arguments environment, the service application name, remote repository, in our case Kate's, and the branch to use for creating a pull request. Since we're following GitOps approach, we would not directly commit to the main branch. Instead, if you want to make any changes to our environment, we create pull requests and let stakeholders review and approve them. After pull request is merged, automation detects the change and takes necessary actions. In our case, this means releasing new versions or pausing and resuming continuous delivery. First, we need to create a file path for each application.yaml file inside each service. For example, this path might look like this. Next, we need to read that file. Remember, you're reading a remote file located on GitHub, not a local file. You need to provide a file path and the branch. The branch will be created from the main branch during this operation. We need a new branch to create a pull request. Then we parse that YAML file and load it into Python dictionary, so we can easily modify certain parts of the application. We pause continuous delivery by adding ignore tags annotation on the application resource and using a wildcard as a value. This tells image updater to ignore every single image tag inside ECR repository. Then we add that annotation to existing application resource that we just downloaded. The key part here is that we're using image aliases, so you must have alias for each image for this to work. Finally, we convert updated application resource with ignore annotation from the Python dictionary back to a file that we can store and update. We also need to write this updated YAML file back to the remote GitHub repo in a new branch that we created for this operation. We can create a commit message in this form. It's also a good practice to log it. In our case, we just print it to standard out. So this is the pause function that would freeze our environment. Alright, we can now freeze environment. We also need a function to unfreeze or resume continuous delivery of all applications in that environment. Let's call this function resume or unfreeze. We're going to have similar steps that you can refactor if you want. First, we need a file path in the remote repo, which is exactly the same as in the pause function. Next, we need to read application.yaml file. At this point, application will have ignore annotation to prevent any updates. Load that file into Python dictionary so that it's easier to work with. This time, instead of adding annotation, we need to remove it from the dictionary using pop method. Then, we need to convert the dictionary back to a YAML file and update it in the remote GitHub repo. Finally, include print statement indicating that we have unfrozen the service. So far, we have pause and resume functions, which allow us to freeze and unfreeze environment on demand. These functions will go over each microservice in the environment, whether you have 2 or 100. Next, let's create a function that will go over each service and collect the latest deployed versions. We typically run this function after freezing environment to test all specific versions together. After testing, you will take these versions and prepare them for the production push. First, initialize empty Python dictionary to store latest deployed versions. Next, get all Helm charts. If you remember, image updater stores newly deployed tags under each Helm chart folder. We need to get all Helm charts to iterate over them and collect versions from every application. In this case, we'll get 2 folders, payments and users. Next, iterate over these folders. Remember that we interact with the remote Git and not with the local file system. For every Helm chart, read argocd-source.yaml file that contains latest deployed versions. Similar to the pause and resume functions, read that file, convert it into a Python dictionary, grab the image tag for that application, and store it in the dictionary with a key representing application. For example, payments 2.5.0. Finally, return versions from that function. Let's also quickly define a function to parse command line arguments, such as environment you want or actions like pause, resume, or push. First, initialize the parser. We will add source-env flag to indicate which environment to use as a base for collecting latest deployed versions. In our case, we will get versions from the development environment. The second target env flag will be used in 2 different use cases. First, it specifies which environment you want to use to prepare a production push pull request with the latest deployed versions. For example, set source env to the development environment and target env to the production environment. The second use case is to specify which environment you want to freeze or unfreeze. We would pause and resume deployments in development environment. Finally, return those arguments back to the caller. Next, let's create a function to perform a production push. This function will take the source environment, for example, development, get the latest versions, and use them to prepare a production push pull request. First, create a target path, such as envs/prod. Iterate over all production applications and prepare a production push pull request. At this point, collect all subfolders under that environment. In our case, it will be payments and users. Then iterate over each of these applications and create a file path to the application.yaml file. For production, use the original application resource to update versions. Next, as always, read each application file from the remote GitHub repository and convert that file into Python dictionary. Create a new params list that will contain all Helm parameters from the application. Go over all of them like image name and health check. Keep all parameters as is and ignore image tag, because we will take the tag from the versions dictionary collected from the development environment. Set the image tag to the latest deployed version. Convert that Python dictionary back into a file and update it in the remote GitHub repo using a newly created branch for that pull request, and print that action to the console. Now, let's create a few functions to interact with Git. First, we need a function to create a new branch. Take the default branch, in my case it's main, and use it to create a new branch and print it to the standard output. In another function, we'll create a pull request. You can potentially modify files directly in the main branch, but it's better to create a pull requests and let someone else to verify those changes before applying them to a live environment. For the pull request, first we need to know the branch name against which we want to create a PR, usually the main or master branch. Then create a pull request and can add a title for that PR as well. Next, we need a function to create a GitHub repo instance. We will use the repository name to find it on GitHub. Unlike simply cloning and updating a remote Git repository using SSH and deploy key, it's not possible to authenticate with GitHub API using that deploy key. There are multiple ways to authorize the client. The simplest is to use a personal token with fine-grained permissions to test it out. We'll create the token later and export it as a GitHub_token environment variable for our script. Next, we use the token to authenticate and authorize with GitHub API. Authenticate means to prove who you are, and authorize means that you have permissions to certain actions. Then we return the repo to the client. That's all the functions we need for the script. Now let's define the main function with core logic. First, create an instance of the repository. Replace this with your repo. Then parse all the script arguments, such as environments and actions. Optionally, get the date to use in the branch name. It's useful to keep production push requests and branches just in case you need to revert if you discover any issues after the production push. Next, create a path for the target environment using command line flag for the environment. It's important to follow the same folder structure because we hardcode some of the values here. Now, here's the core logic. First, let's create steps for the pause function or freeze function, which would pause continuous delivery. First, create a new branch. Use the following pattern: action, in this case pause, dash, environment name, and today's date for the branch. Then make necessary API calls to the GitHub API to create that branch. Next, get all applications from that environment. In our case, we have payments and users. This step only gets subfolders under the target environment. Next, iterate over each folder with application and call our pause function. This step adds ignore annotations to all applications in the environment. All those updates are done in a new branch that we created. So the next step is to use that branch created for this action and create a pull request. We can add a title like freeze development environment. That's all for the pause function. Next, let's create steps for the resume function. It's going to be very similar to the pause function. Create a name for the new branch, this time using resume prefix. Then create the branch in the remote repo. As in the previous step, iterate over each application and apply resume function to remove ignore annotation from the application resource. Then create a pull request with those changes. Finally, let's create steps for the push function. Give a new branch a name like prod push. Create a new branch. Get the latest deployed versions from the source environment. Then use update function to replace current image tags with new ones collected from the development source environment. Finally, create a pull request. That's all. By convention, use internal main variable, and if you execute this file directly and not as a module, run the main function. We need to make this file executable to use it without Python command. Now, we still need to authorize the script to make GitHub API calls. So let's create a token with granular permissions. Go to GitHub settings, then developer settings, and create a personal access token. Name it something like Kate's GitOps. Select the private GitHub repo, in my case it's Kate's repo, where I have all the applications for Kubernetes. For permissions, select contents to read files and create commits. Also, we need permissions to create pull requests. That's all, create this token. To provide this token to our script, export it as environment variable. Before running the script, let's tail updater logs again. To freeze any particular environment, select it by using target environment option and pause action. When you run it, this script will create a new branch, start making changes to files, and commit them back to that branch. It adds ignore annotations to payments and users' applications. And at the end, it creates a pull request with those changes. Let's go back to Kate's repo and open that pull request. As you can see, it updated 2 files. In the real world, the main branch will be protected and will require at least one additional approval besides yours to merge. You would share this PR on Slack or MS Teams and wait for your team members to approve it. When the pull request is approved, you can merge it to the main branch. Double check that we have ignore annotations. We have one in payments microservice and a similar annotation in users. Don't forget that you need alias for the image name in the annotation. Keep in mind that ArgoCD has 3-minute sync cycle. You can either wait until ArgoCD applies those changes automatically or click sync button if you don't want to wait. Double check that we have those annotations. You can see them in the UI for both the payments and users' applications. At this point, our development environment is frozen, and no new images will be deployed in that environment. The best way to verify this is to wait for the next image update cycle, which happens every 2 minutes. Let's test this by pushing new image tags to the ECR. Create 2.5.1 image tag for the payments and 0.5.1 tag for the users' application. Push the payments image and do the same for the users. Verify in the ECR that we have new tags for both images. Now, we just need to wait for the next update cycle. If the image updater ignores those new tags, it means we successfully paused all the deployments in the development environment. From the logs, you can see that the new tags were ignored, and there are no new commits from the image updater in the K8s repo. The last version remains 2.5.0 and not 2.5.1 for the payments, and similarly for the users. Now it's time for the production push. This means we take a snapshot of versions, usually from the staging environment, but in this case from the frozen development environment, test them and push those same versions to production. Currently, we still have initial 0.1.0 versions in production environments for both payments and users. Remember, for production environments, we hard-coded application versions directly in the application.yaml file. Our script will prepare a pull request to update those versions. This time, when we run GitOps script, set the source environment to development and the target environment to production and use push as the action. It will follow the same logic, create a new branch in the remote repo, update versions in that branch, and finally create a pull request. In GitHub, you will find a new pull request. This PR updates versions from the source environment. Share this PR with those responsible for the production push and wait for the approval. Then perform production push when there are the least number of active clients and avoid doing it on Friday. Otherwise, you may have to spend weekend debugging production environment. Keep this PR somewhere in case you need to quickly revert if it breaks your production environment. After merging, verify that you have new versions in Git. Wait for the apply cycle or click the sync button. I'll speed up the time. It took around 4 minutes for ArgoCD to apply those new images in production environment. In the ArgoCD UI, you can also check the versions deployed in the production environment and see the new versions. Now, let's say we performed a successful production push with no issues. Next, we can unfreeze our development environment to continue developing and deploying new features. We already have 2.5.1 version for payments and 0.5.1 version in ECR for users, so the development environment is slightly outdated. These are the new image tags in ECR. In the image updater logs, you can see that it still ignores those tags. Let's go ahead and unfreeze development environment. The action is called resume, and the target is development environment. Review the PR and merge it into the main branch. This PR removes ignore annotations from all applications in the development environment. wait for the ArgoCD to release new versions to the development environment. It may take some time since ArgoCD first needs to apply applications. Then the image updater needs to detect new ECR images, make commits, and finally ArgoCD will apply those new versions to Kubernetes. Let's see how long it takes without manually synchronizing Git. From the logs, you can see new image tags were detected and committed to Git. So we can have a couple of new commits with fresh application versions. In about 6 minutes from the PR being merged, we have resumed continuous delivery to the development environment. Don't forget to delete branches on merge or clean them up periodically if you perform frequent pushes. I have other ArgoCD tutorials that cover more features, as well as many other tutorials for Kubernetes, Docker, Kafka, and benchmarks. Thank you for watching, and I'll see you in the next video.